Hello everyone and welcome to today's presentation. I'm excited to introduce our topic, machine learning, with a focus on support vector machines. Introduction. Over the course of this presentation, we'll cover the core principles behind SVMs, how they work for classification and regression, and why they are such a powerful tool in machine learning. Let's get started. Let's take a closer look at the support vector machine, or SVM for short. As you can see in this illustration, the core idea behind SVM is to find the best way to separate different classes of data points. Imagine these points as different groups that we want to distinguish clearly. The SVM aims to draw a boundary, or a hyperplane, that maximizes the margin between these groups. This margin is essentially the distance between the closest points of each group to the boundary. By maximizing this margin, the SVM ensures that the separation is as clear and robust as possible, which helps improve the model's generalization to new data. The most important concept here is that the SVM doesn't just look for any boundary. It seeks the optimal one that offers the best separation. This makes SVM very powerful, especially in cases where classes are not linearly separable, as it can be extended using kernel functions to handle more complex data distributions. Connecting this to our overall theme, understanding how SVM finds this optimal boundary is fundamental because it highlights the strength of margin-based classifiers in creating reliable, high-performance models. Let's dive into some key concepts that form the foundation of SVMs. First, we have the hyperplane, which you can think of as the decision boundary that separates different classes. In a simple linear classification, this boundary is represented mathematically by the equation WT plus B equals 0. This hyperplane is crucial because it defines how we distinguish between the classes. Next, support vectors are the data points that are closest to this hyperplane. They're actually the most critical points because they determine the exact position and orientation of the hyperplane. In fact, the entire margin, the space between the hyperplane and these support vectors, depends on them. Speaking of the margin, it's basically the distance from the hyperplane to the nearest support vectors on either side. Our goal with SVMs is to maximize this margin, because a larger margin generally leads to better generalization on unseen data. Finally, we have the kernel function. This is an elegant tool that maps data into a higher dimensional space, which allows the SVM to handle data that's not linearly separable in its original form. By doing so, kernels enable us to find a separating hyperplane even when the data is more complex. All these concepts, hyperplane, support vectors, margin, and kernel, are interconnected. Together, they help us understand how SVMs can effectively classify data, even in challenging scenarios. Let's take a closer look at this illustration, which shows a support vector and a hyperplane. The hyperplane is essentially the decision boundary that separates different classes in our data. It's like a line or a plane that helps us distinguish between categories. The support vectors are the data points that are closest to this boundary, and they play a crucial role because they define the position and orientation of the hyperplane. Think of them as the most influential points in shaping our decision boundary. Highlighting these points helps us understand how the model makes its decisions. This concept is fundamental to understanding how support vector machines work, as they aim to find the optimal hyperplane that maximizes the margin, the distance between the support vectors and the hyperplane itself. This maximization improves the model's generalization ability. So, in essence, the support vectors and the hyperplane work together to create a robust and effective decision boundary, which is at the heart of what makes support vector machines a powerful classification tool. Now, let's take a closer look at some key concepts that extend our understanding of SVMs. First, the kernel trick. When our data isn't linearly separable in its original space, SVMs can still find a way to separate it effectively. They do this through the kernel trick, which involves using kernel functions like linear, polynomial, or the radial basis function, or RBF. Essentially, these functions allow us to implicitly map our data into a higher dimensional space, where it often becomes linearly separable. This means we can find a hyperplane that separates the classes more easily, even if it wasn't apparent in the original space. Next, we have the idea of a soft margin. In real-world scenarios, perfect separation isn't always possible or even desirable. Noise and overlapping classes can make strict separation problematic. That's where the soft margin comes in. It allows for some misclassifications or margin violations, which actually helps make the model more robust and better at generalizing to new, unseen data. So, instead of forcing a perfect boundary that might overfit, the soft margin provides a more flexible approach that balances accuracy and robustness. Together, these concepts, kernel trick and soft margin, are crucial because they help SVMs handle complex, real-world data more effectively, aligning with our overall goal of creating models that are both accurate and resilient. All right, let's dive into how SVMs actually work. For classification tasks, SVMs aim to find the best possible decision boundary, which we call a hyperplane. This boundary is constructed to optimally separate the data points belonging to different classes. The key idea here is that the algorithm identifies certain data points, known as support vectors, that are closest to the boundary. These support vectors are crucial because they define the position and orientation of the hyperplane, and the goal is to maximize the margin. That is, the distance between these support vectors and the hyperplane itself. By maximizing this margin, the classifier becomes more robust and better at generalizing to unseen data. Now, SVMs aren't just limited to classification. They can also be adapted for regression tasks, which is called support vector regression, or SVR. In this case, instead of separating classes, the goal is to find a function that predicts a continuous target variable. The SVR tries to fit this function within a specified margin of tolerance, meaning it allows some errors but keeps them within acceptable bounds. This flexibility makes SVMs quite powerful across different types of predictive modeling. Overall, what ties this together is the core idea of finding an optimal boundary, whether it's a hyperplane for classification or a function for regression, that balances accuracy with generalization. That's what makes SVMs such a versatile and effective tool in our machine learning toolkit. Now, let's take a closer look at the different types of support vector machines, or SVMs. Essentially, SVMs are versatile tools in machine learning, capable of handling various kinds of data and tasks. The most common type is the linear SVM, which is used when your data is linearly separable. It finds the best possible boundary, or hyperplane, that separates the classes with the widest margin. But in many real-world scenarios, data isn't perfectly linear. That's where the kernel SVM comes into play. It transforms data into higher dimensional spaces using kernel functions, allowing us to find nonlinear decision boundaries. This flexibility makes kernel SVMs powerful for complex classification problems. There's also the concept of soft margin SVMs, which introduce some flexibility by allowing certain misclassifications. This is particularly useful when data is noisy or overlaps, helping to prevent overfitting. Overall, understanding these different types of SVMs empowers us to choose the right approach for our specific problem, ensuring better accuracy and robustness in our models. Now, let's look at the main division of support vector machines based on the nature of the decision boundary needed for separation. First, we have linear SVMs. These use a straight line, or in higher dimensions, a hyperplane, to separate the data. They're particularly suitable when the data is linearly separable, meaning it can be divided by a single straight line in 2 dimensions or a hyperplane in more dimensions. The primary goal here is to find that hyperplane that maximizes the margin, which is the distance between the decision boundary and the closest data points on either side. On the other hand, we have nonlinear SVMs, which are used when the data can't be separated by a straight line. This is where things get more interesting. Instead of trying to find a linear boundary, we use kernel functions, sometimes called the kernel trick, to transform the original data into a higher dimensional space. In this new space, the data becomes linearly separable, allowing us to draw a hyperplane that separates the classes effectively. This approach is powerful because it enables us to handle much more complex, nonlinear relationships within the data, while still leveraging the core principles of SVMs. Let's talk about some key advantages of support vector machines. First, they are highly effective in high-dimensional spaces, which means they can handle data with many features without losing their accuracy. This is especially useful in fields like text classification or genomics, where data can have thousands of attributes. Second, SVMs can handle nonlinear data quite well, thanks to the use of kernel functions. These kernels transform the data into a higher dimensional space where it becomes linearly separable, allowing the SVM to find a separating hyperplane more effectively. It's a powerful way to capture complex patterns without explicitly computing those high-dimensional mappings. Third, SVMs are robust to outliers and noise, especially when using a soft margin approach. This means they can tolerate some misclassifications during training, which helps prevent overfitting and makes the model more reliable when working with real-world, imperfect data. Overall, these strengths make SVMs a versatile choice in many machine learning applications, aligning with our goal of building accurate and resilient models. Now, let's talk about some of the limitations of SVMs that you should keep in mind. First, they can be quite computationally expensive, especially when you're working with very large datasets. This means that training an SVM might take a significant amount of time and resources as your data grows. Next, the performance of an SVM is highly sensitive to the choice of kernel and hyperparameters. Selecting the right kernel function and tuning these parameters is crucial. Otherwise, you might not get the best possible results. It's almost like finding the right settings on a complex machine. Small changes can make a big difference. And finally, unlike some other models, SVMs don't provide a probabilistic interpretation of their classification output. So, if you need to understand the confidence level of a prediction, SVMs don't inherently give you that information. These points highlight some important trade-offs when choosing SVMs as your machine learning tool, especially in terms of scalability and interpretability, which are key themes in understanding when and how to best apply them. Thank you for watching. Like, share, subscribe to EC Learning 360 YouTube channel.